Hey y'all, today we're going to be talking about section 2.2, which will be pretty similar to last section, except for instead of qualitative data, like 2.1, we're going to be organizing quantitative data in 2.2, which quantitative will be numbers. So, let's dive in. First and foremost, maybe even before you read this slide, I probably should question it before. Oh well, we're doing it now. Do you think that you could do bar graphs or Pareto graphs with numbers? Maybe like the amount of people that walk in a restaurant? Do you think you could organize the amount of people that walk in a restaurant via tallies, via proportions, and order it in some way and use pie charts and such? Yeah, turns out you can. Quantitative data is largely no different than qualitative data in as far as how we display it. There will be minor differences, as you will see, but I just wanted to say it will be a lot of the same things. So if you haven't understood 2.1, now's your time to go back because yet again, quantitative data can be summarized by a lot of the same methods. Well, let's dive into the official how-to. First and foremost, when given quantitative data, number data, you first have to determine if the data is discrete or continuous. Remember that discrete meant that there were gaps between successive answers versus continuous meant that there were no gaps. So discrete, we thought of number of people in a room at a given time. Something like 2.5 makes no sense there. Continuous, we thought about something like height or weight. For instance, with weight, could I weigh between 216 and 217 pounds? Well, yeah, I could weigh 216 and a half, and so on and so forth. Now, if the data is discrete, meaning there are gaps between numbers where there's no answers in between, well, if there are only a few different options for answers, turns out just use the tools of section 2.1. Literally just treat each answer or number as a category and do the exact same thing with your frequency and relative frequency distributions. Now, it turns out if there are many different answers, you don't want to take a category for every single answer. That would be a ton of answers. Well, at that point, we can split the data into intervals. So, something to compare it to in last section would be if I was talking about every country in the world. Well, that's a lot of answers. Maybe I just want to split it into continents. That's what we'll do with numerical answers. We'll take all of these number answers and we'll split it into intervals or ranges of numbers. Now, it turns out, by the way, if you're continuous, we're just going to split the data right away. There's just too many answers. You can't list them all. Now, instead of the word categories like last section, I'll be calling these classes this section. I might trip up and call them categories, but we should be using the word classes when talking about quantitative or number data. Now, instead of doing bar graphs, what we'll do for quantitative data is histograms. Now, histograms are very similar to bar graphs, except for, like I said, they're used for quantitative data. Now, before I dive into the other two bullet points, here's what a histogram is. Does it look like a bar chart? Yeah, 100%. Well, not 100%. If I go back to my bar charts, notice that there are gaps between to separate my categories. If then I fast forward to histograms, there will be no gaps. This signifies that numbers are kind of inherently closer versus something like red and blue. How close are they? That's kind of a weird thing to think about. So histograms are touching bar graphs. So a histogram, to be formal, is constructed by drawing rectangles for each class of data, and the height represents either the frequency or the relative frequency. And like I said, rectangles touch when you're doing histograms. Now, since we already got very good at making bar graphs in our last section, well, histograms are basically no different, except for notice, say on the right-hand one over here, my categories, in this case classes, are numbers. So my possible scores were 1, 2, 3, 4, and 5. And boom, there are the bars for each. Notice this is a frequency histogram, because we're representing frequency on the vertical column, or the vertical axis, excuse me. Now the right-hand one would be an example of discrete data. There were only 5 possible scores, so discrete data with very few options. That's why we went ahead and just listed out every single category on the horizontal axis or class, and then we did the frequency on the vertical. Now on the left-hand histogram, notice this is a frequency histogram. We're dealing with numbers on the vertical axis, not percentages. But we're dealing with tree heights, which is continuous data. You could be any height in between any two numbers. Therefore, instead of giving, say, a name to this class right here that I've underlined, we're considering that class to be the range of answers from 100 centimeters tall up to 150 centimeters tall. So if you were 127 centimeters tall, congrats, you counted towards that count. Now let's look at what our classes are. Our first class is 100 to 150. Our second class would be 150 to 200. Our third is 200 to 250. Our fourth is 250 up to 300. And our last is 300 up to 350. If you were, say, 272, you would fall into this class and count towards that height on the histogram. Histograms, not too bad. And that's the difference between discrete data with small answers and continuous data. Now let's go ahead and do the following. Construct a relative frequency histogram representing the following data for customers arriving at Wendy's. Okay, so we got a ton of data. Maybe this is customers within an hour arriving on given days. So 7 customers, 6 customers, 6, 6, 4, 6, 2, 6. Keep on going. Whew. Now remember to do a relative frequency diagram or chart, which was helpful in creating a bar chart. What you wanted first off was a frequency histogram or chart. So instead of getting relative right away, let's get our frequency histogram, or chart, frequency chart. In order to get a frequency chart, I need to know how many 6s there are on the board, how many 4s, how many 5s, so on and so forth. It's going to be a lot of work. Now, in order to negate that work, I went ahead and made the frequency chart for you guys. So, woohoo! Now, since I'm wanting to make a relative frequency chart, I'm actually just going to tack on an extra column right here. So allow me to do that right now. And then we'll end up translating these relative frequencies into a actual histogram. Oh, it looks ugly. Looks like my face. Okay, great. Now we got the relative frequency chart ready. Well, what percent does 1 represent right here? Well, just like last section, in order to get towards the relative frequencies, we do have to figure out the total number of items that were, or things that were observed. Now I'm going to go back to this. Notice we have 1, 2, 3, 4, 5 rows. We have 1, 2, 3, 4, 5, 6, 7, 8 columns. So I do 8 times 5, and this gives me a sample size of 40. If you so wanted, just like last time, you could add up 1 plus 6 plus 1 plus 4 plus 7 plus 11 plus 5 plus 2 plus 2 plus 0 plus 1, and you would also get 40. Take this n value, which is our sample size, and divide each item by it. So we would divide all of these by 40. I'll stop right there just for timing's sake. If I do 1 over 40, I get 0.025. 6 divided by 40 is 0.15 or 15%. 1 over 40 we already did, 0.025. 4 over 40 is 0.1, 10%. 0.10 I'll do. And 7 over 40 will be 17.5%. 0.175. Now you can keep going with this if you want it, and you can fill out the rest. I'm just going to make the relative frequency histogram for the top 5 values, as to save for time. So complete that process out to get your relative frequency diagram. Notice that we're wanting a relative frequency histogram though. Now in this case, we are dealing with 11 different classes. That's kind of on the border between being too many and having enough to list it all out. I'm going to advocate that you list it all out in this case. So what does that look like? Well, like I said, I am only going to be doing the first 5. So I'll have 1, 2, 3, 4, 5, and I'll do a ... because you go up to 11, the number of customers. And in fact, I'll label that down here. Number of customers, boom. And on the left hand, the vertical axis, we're going to want the relative frequencies. So relative frequencies over here. Now to pick out good numbers, we'll start at 0 on the way bottom. Just pick numbers that seem pretty good. And now what I'm going to do here is I'm going to say, hey, let's call this 0.05. We'll go 0.10, 0.15, 0.20. I'm going up by 0.05s. Now that you've got it clearly labeled, and you could keep going vertically as well as horizontally to complete out the rest of this chart, all I'm going to do is to say, well, wait a second. Number of customers being 1 corresponded to 0.025. That is halfway up this. So, boom, there's my first bar. Number of customers being 2 corresponded to, wow, 15%. So that goes way up here. And hey, our bars will touch. So it looks something like that. For 3 customers, that was a 0.025. So we dropped pretty drastically again down to the height of 0.025. 4 customers was 0.10. So hey, that's kind of a nicer one. We go up to 0.10 and over, making sure our bars touch. And last but not least, 5 was 0.175. So we go up to 0.175. That's halfway between here. Making sure everything's touching. Hey, that is the tallest block for right now. And shade it in. And that's what a relative frequency histogram will look like. Just like a bar graph, except for it's touching. Making sure everything is clearly labeled for me to see on exam day. Now, as I've already kind of mentioned for this chapter, classes are going to be the categories of quantitative data. So classes are categories into which data are grouped. Not too bad, just another word for category. Now, when we deal with these classes, it's kind of helpful to have some terminology down. So for instance, when we're actually splitting the data into intervals, when we have either continuous data or discrete with many values, turns out we have to have some numbers pretty well defined. For instance, we have to have the lower class limit, the upper class limit, and the class width. Those are all notions that we're going to want to have down. Now, what are they? The lower class limit will just be the smallest value in your class. The upper class limit, therefore, will be the largest value within your class. And last but not least, the class width is the difference between consecutive lower class limits. If I go back to my tree example, which is of course all marked up, if I pick on the one with the star on it, my lower class limit, I'm not talking about cholesterol levels, my lower class limit for this one right here would be 250. My upper class limit you would think would be 300 because that's what we bump up to, but we're actually going to probably list 299. The reason we're going to list 299 is because ultimately, let's say we had a tree that was exactly 300 centimeters tall. Well, which one should it go in? 1 or 2? So in order to well define this chart, we're going to say that the lower class limit of 1 starts at 250 and includes everything just short of 300. So if you're familiar with less than equal to, we're talking about 250 up to 300, but not including 300. That's why we list an upper class limit of 299, meaning we're also including, say, 299.4 in it. Last but not least, our class width is just how the difference between consecutive lower class limits. So as you guys would kind of imagine, each class contains 50 different numbers that you could be to get in there. So class width of 50, and that's just the difference between, say, 100, 150, 150, 200, so on and so forth. So that is an important thing with class width, is it's the difference between consecutive lower class limits. Now, importantly, class widths must be equal. If you're giving me unequal class widths, I'm going to think that you're doing something kind of screwy with the data. I'm going to think you're manipulating it in some way. Therefore, in order to be unbiased, we're going to keep the class widths the same. For instance, with trees, we had them all 50 centimeters in class width. Now, there are two exceptions to this, and the only exception will be if the table is open-ended. Now, the two exceptions, if the table is open-ended, would be that the first class has no lower class limit, meaning there's kind of an infinite range of negative values potentially. And it turns out the last class will have no upper class limit, meaning, hey, we're just including everything to the right of a certain number. Now, as we already got at, it's important that our classes do not overlap. So this is very, very important, because if there was any overlap, even if my classes were, say, 150 to 200 and 200 to 250, it brings up the question of where does 200 go? Do I go in this one or do I go in this one? That's why typically in these scenarios, we're going to write our classes. So instead of this, we'll write our classes as 150 up to 199 and 200 up to 249 if we kept going. That way it's unambiguous where your border values will go. Now, if you have like 199.4, just adhere to your typical rounding rule. 199.4 would go in my top category versus 199.7. Well, let's round that up to 200. Bam, there you go. Excuse me. Now, you won't really have to do this, but I do think it is good to know, because since I'm telling you, hey, class widths must be equal, and hey, if you have too many options, then use intervals. Well, it brings up the question of how the heck should I do that? Here's some guidelines for setting up these histograms and these different intervals. So to choose a good lower class limit of your first class, either, well, choose the smallest observation in the data set. So for instance, if I am doing IQ scores and the smallest one is 85, maybe I start at 85. Maybe I start lower though, because the second option is to choose a convenient number slightly lower than the smallest observation. Now, largely you want to do this when you have an observation like 8.28. Just pick 8 as your lower one. It's nicer to read and it's kind of more intuitive. You don't always have to round to a whole number or start at a whole number. Maybe you always want to start at either a number that ends in 0 or 5. So kind of up to you how to pick it, but take either your smallest or take something slightly smaller that's convenient. Now, in order to choose, by the way, the same goes to, say, a good upper class limit as well, would be to kind of pick something that is either your highest or something conveniently above in that case. But maybe most importantly, hey, how do you choose a good class width? Well, first off, decide on the number of classes you want. So once you have a good lower class limit, choose the number of classes that you want. Typically, we keep that between 5 and 20. Fewer than 5, and it's just kind of too clunky looking. It's not really fine enough. But if you get more than 20, then all of a sudden it's kind of lost within the data. It's almost too fine. It's like looking at an elephant through a microscope. Doesn't really make much sense. So between 5 and 20. And once you have the number of classes that you're after, say you're after 7 classes. So once you have that, go ahead and calculate your class width by taking your largest observation minus your smallest observation and dividing by the number of classes you want. Once you do that, round up. So let's say my largest observation was 100, my smallest was 0. To get the number of classes, if I want 7, I would do 100, take away 0, divided by 7. You bet I'm going to a calculator. 100 over 7 is 14.28. So my class width here would be 15, since we round up no matter what. Now, as a visual example, and we already talked about this, hey, what are the lower class limits of the following graph? What are the upper class limits? And what are the class widths? Well, class width, we've already talked about, is 50. You take 2 consecutive lower class limits, subtract them. So 150 take away 100. Hey, that's 50 all day. You didn't have to take the first 2. You could have done 300 take away 250 to get 50 as well. That should be consistent. My lower class limits here will be 100, 150, 200, 250, 300, and not even 350. Notice that we kind of stop at 350. We don't have anything to the right of 350, so that's not the bottom number for a class. So 350 is not a lower class limit, it turns out. My upper class limits, on the other hand, will be 149. That's the last number to appear in this one. It'll be 199, the last number to appear in my second rectangle. 249, 299, and 349. Notice when I combine all of these numbers, I get my 5 boxes that appear on the graph. So just be careful on upper class limits. It's not the number that appears on the graph. It's usually one down from that number. That way you don't have overlap, as we talked about. Now, I did give you this video in your notes to check out. This is good Excel functions. We are going to start using Excel, and you'll actually see me do a little bit of this today. But it turns out this video right here is very helpful for actually giving you the basics as far as summing data, meaning, hey, you can take a list of numbers and add it for free in Excel. You can organize data. So if I give you something messy like this, you can put it in order and make it not so messy. It'll give you the way to count data, and it's kind of just an all-around good introduction to Excel. So please click on that link. Now, if you don't have Microsoft Excel, don't worry. By being a part of this university, you can get Excel for free, actually. So click that link. It'll take you to a PDF describing how to download Excel, or at least the online version. And you'll get Office for free with it. So you'll get Word and PowerPoint and all that sort. Now you're going to see my first go at using Excel. So I won't be in this screen presentation mode, so bear with me here. The data below represents the number of the number of customers waiting for a table at 6 p.m. for 40 consecutive Saturdays at Bobox Restaurant. And hey, notice we have 40 consecutive Saturdays. We were given that for free. So I know n equals 40. Well, let's see what it asks. Is the data discrete, continuous, construct? Oh my goodness, we got a lot. Let's just start with the first one. Is the data discrete or continuous? Notice that since we're talking about number of customers waiting for a table, well, that will be discrete. You're not going to be dealing with 5.5 people waiting. That half makes no sense when talking about customers. So in this case, the data is discrete. And, we have quite a bit of different options here as far as categories. For instance, you could be as low as 3, but you could also be as high as, say, 15. So, let's go on to the next question. Construct a frequency distribution with class width 3 and first lower class limit of 1. Here's where I'm going to go ahead and dive out for a little bit. So, in order to do this, especially if you have the PowerPoint up, I have made these in a table. So what you can do is copy this table. I do have Excel up and paste it here. Now, if it looks like I did nothing, yeah, that's on me. The font in the PowerPoint is white, but notice that if I take it black, then we're good to go. Let me size this down to something not so bad, and I always like, I guess, Arial or Calibri. Let's go with that one. Now, there's my table. Now, what I'm going to go ahead and do is I'm going to put all of these in one column. So I'm just going to copy paste everything. You highlight, and I'm doing Control C, Control V. Whoopsies, I actually copied that one. I wanted to just cut it. So if you want to cut, you could also probably do that here. But highlight, Control X, Control V. It works just like a Word document. Control X, Control V. I know this is probably the most exciting part of the video. Control X, Control V, Control X, Control V. And yes, we're very close to being done. Thank you for your patience on this. Control X. Oh no. What'd it do? Oh, I accidentally clicked on too many things. Let's say Control X. Let's go back down to here and Control V. Whew. Okay. All I did is I took this table that was over here and I plopped it all in one column. By the way, this is the Excel, I guess, landscape. This is what Excel looks like. You have a bunch of columns labeled with capital letters. You have a bunch of rows labeled with numbers. The first nice thing to notice is your rows are actually labeled. So notice I'm starting with 1, and I go down all the way, in this case, to 40. That actually just tells you right away, hey, I had 40 observations. So, hey, kind of nice. Now, since we're making a frequency distribution, well, what would be nice is this all being ordered. Right now, when it comes to 12 customers waiting, I'm going to need to find the number 12 in here a lot of times. That's time consuming. Instead, what we should do is highlight the data, click and drag, and it turns out there's this handy sort and filter thing over here. Notice I can sort from both smallest to largest and from largest to smallest. Let's go smallest to largest. Cool. Got it ready. Now let's look at what the question was telling us. Okay, we are on this question right here. Construct a frequency distribution with class width 3 and first lower class limit 1. Now I'll pull this up. I'm also not going to pull that up. Let's pull this up, which is going to be my whiteboard. So we're getting all the tools going today, y'all. Now I wanted my first lower class limit to be 1. So let's say classes, because I'm making just a distribution right now, not a histogram. And let's go frequency. And for good measure, because I ask it in the next problem, let's go relative frequency to the right of it. Now I want my first lower class limit to be 1. That just means I'm starting at 1 here. Now my class width will be 3. We calculate the class width by taking the difference between consecutive lower class limits. So my lower class limit for the next one will be 1 plus 3, so it will be 4. This tells me my upper class limit will be 3.9, which, doesn't quite make much sense for humans. So what we could do is 1 to 3. If it were continuous data like tree height, you might say 3.9, but let's just do 1 to 3. Notice, by the way, that includes 3 numbers, 1, 2, and 3. Okay, so my next class will be starting at 4, 5, and 6. So it'll be 4 to 6. Then we'll do 7, 8, 9. 7 to 9. 10 to 12. And then how many classes are we doing here? Let's go 13 up to 15. We can check the wording of the problem. Hey, it doesn't tell us how many classes to do. So instead, what we need to do is go to our data and say, okay, good. There's only 15 bits of data. So we've captured absolutely everything that will appear in here. Great, let's keep it at this. Now remember, our class width is how much will be included in each class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Class width of 3. The lower class limit just told us where to start counting. Okay, great. Let's go back to our Excel. Now our first class is all answers that have either values of 1, 2, or 3. If I go here to my list and I count 1, 2, there are only 2 3s on the table. So for this, I would put 2 for my frequency. There were 0 1s and 0 2s, and there were 2 3s, so my frequency in that class is 2. Now, how many times do numbers between 4 and 6 show up? Well, let's start counting. 1, 2, 3. Okay. Not too bad. 3. How many times do numbers between 7 and 9 show up? Well, in this case, we do 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 for 7 through 9. Next class, 10 through 12, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, 17. Wow. And last category, 13 through 15, we have 1, 2, 3, 4, 5, 6. So 6 goes here. By the way, real quick, notice if you add all these up what you get. 2 plus 3 plus 12 plus 17 plus 6 gives you the total sample size back. You can always do that to gather the total sample size. Now, just to throw a what if and to take a pause in the problem, what if you had a lot more numbers in here? Well, turns out Excel's pretty nice. Just to flex for a second, and I'll show you how to do this later, let's go back to that 10 through 12 category, which had 17 things, kind of easy to get tripped up. If I just do a command, which we'll talk about later, equals count, and if I just highlight all my numbers between 10 and 12 like that, wow, it tells me that there are 17 numbers in there. You might have also been kind of smart and said, hey, what if we do something like 35 minus 18, something like that, and voila, you should get 17 from there as well. So there are plenty of tricks in Excel That was a brief pause. But, bam, there is our frequency distribution that they asked for. Now notice the next question right here. They ask for a relative frequency distribution. So all we're going to do, since the class width and lower class limit are the same, is we'll take this stuff that we found and we'll convert it to a percentage. It was important that we found out our sample size was 40, because now if we divide each number by 40, so if we do like 2 divided by 40, we'll get 0.05. 3 over 40 is 0.075. 12 over 40 is 0.30, 30%. 17 over 40 is going to be 0.425. And 6 over 40 is 0.15. Bam, there's our relative frequency distribution. Okay, now let's get into some questions that they're asking us from this. So I will go ahead and punt on these two. They says construct a frequency histogram and construct a relative frequency histogram. All you would do, for instance, on that one would be to do something like, for our frequency, let's go our frequency histogram. You would start with different classes, say 0 right here. So 1, 2, 3, 4, 5, 6. 1, 2, 3. Apologies, let me get this right. 1, 4. So list out your consecutive lower class limits. 1, 4, 7, 10, and 13. So let me go ahead and do this actually. In order to do a relative frequency histogram for this type of data, first off, list out all of your lower class limits. 1, 4, 7, 10, 13. Which you can see I did here. Feel free to list out your last upper class limits, like 16. Or your last lower class limit. And then all you're going to do is clearly label here. So maybe we count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. And then notice for the group between 1 and 3, we had 2. So that takes up right there. Between 4 and 7, so that's 4 to 6, we had 3. That's just a smidge higher. Between 7 and 9, or 7 to 10, for lower class limits, we had 12. So we kind of bumped that way up to here. Between 10 and 13, or 10 to 12, we had 17. So we bumped way up to the top as well. So we got like this. And then last but not least, between 13 and 15, meaning a value of 15.4 would have been down. That's why I included 16 right here. We had 6. So we get something like that. So that's how you take this data from a frequency diagram as far as classes are concerned. And that's how you translate classes to a frequency histogram. You would do the same thing with relative frequencies, just with a different vertical axis labeling. Just the important thing is the numbers that show up right here, all of these numbers are your lower class limits. So that is important. That's why I wanted to pause and go through that. Okay, apologies for the delay. Let's go back to the question. What percentage of Saturdays had 10 or more customers waiting? Interesting question. Well, since it's talking percentages, let me drag this over so we can see the question as well, if it wants to. There we go. So 10 or more customers waiting on Saturdays. Notice the 10 or more in this case is talking about these guys right here. 10 up to 15. Well, 42.5% would be between 10 and 12, whereas 15% would be between 13 and 15. So if we wanted 10 or more, we want both of those categories. All we have to do is add 0.425 plus 0.15. Now, if we do out that math, notice the decimals line up that way, we'll get 5.0. Or if you want to put it in percentages, we'll have 57.5%. So 57.5% will have 10 or more customers waiting. That came by adding these two together. Yes, 57.5%. There we go. It's been a long day, y'all. Whereas if you wanted to do what percentage of Saturdays had 10, 12, or fewer customers waiting, well, all you'd have to do is look at for your categories that have 12 or fewer, which in this case would be 12 or fewer. And you can just add all of these together. If you add all of these together, it turns out you'll get 0.85, which is 85%. Handy little trick that will come up. If you wanted to do 12 or fewer, instead of adding all of these categories together, if you wanted to be smarter, you could have said, well, wait a second. Since I know if I add everything up, it gives me 1, I could have done 1 minus 0.15 to give me 0.85. So add all the things in red together to get 85% directly, or do 1 take away the other categories, 0.15, to get 85% of Saturdays will have 12 or fewer customers waiting. And like I said, we already took the time to do a frequency histogram. Relative frequency is the same thing, just with different labeling on the vertical axis. Second to last thing we'll talk about in this chapter, in this section, will be shapes of distributions. Now, we're going to be obsessed over bell-shaped distributions later on, but it is important that distributions come in different shapes. By distributions, what I'm really talking about are like bar graphs in a way. So you could have bar graphs that all have the same height, bar graphs that peak in the middle, bar graphs that peak on the left but kind of tail off to the right, and last but not least, the vice versa of that, bar graphs that peak on the right-hand side and tail off to the left. Here are our technical names. We say that a distribution is uniform if each frequency has the same value. That just means the bars all have the same heights. We'll say that a distribution is bell-shaped if the highest frequency is in the middle and you tail off to either side, so it'll look something like this, or like that for uniform. Confusingly, so pay attention, we'll say that a distribution is skewed right if the tail to the right of the peak is longer than the tail to the left. When I say skewed right, what I mean is my peak is more towards the left-hand side. So it'll be something like that. If I say skewed left, that is if the tail to the left of the peak is longer than the tail to the right. So when I say skewed left, what I mean is your peak is on the right-hand side of your data, and then you kind of trail off something like that. So skewed left meaning longer tail to the left, skewed right meaning longer tail to the right. By the way, just like I emphasized, bell-shaped distributions will be very important later on because they represent a wide variety of data. For instance, marathon race times, you could say, standardized tests, you could say heights are represented via bell-shaped distributions. And just to give everybody a glance, shapes of distributions, well, symmetric, that will be called bell-shaped, or normal, we'll call it later. So it looks uniform, hey, everything's the same height. Think like army uniform. Skewed left, hey, the tail to the left is longer than the tail to the right. skewed right, the tail to the right is longer than the tail to the left. Last thing, just in case you thought this section was too intense for your liking, let's end on something nice. Turns out you can do dot plots to represent data. Dot plots are similar to histograms, except for instead of bars, you just use dots to represent how many observations are there. So, for instance, in this kind of funny example, I represented minutes to eat breakfast out of a total number of observations, and each dot represents one different observation. So there were 5 times that it took me 5 minutes to eat breakfast. There were 0 times that it took me 6 or 7 minutes to eat breakfast. There was only 1 time it took me 12 minutes to eat breakfast, so on and so forth. Obviously, the nice thing about bar graphs, histograms, and dot plots is that you'll naturally see different distributions arise from them. Notice these are all histograms right here. So you can see a bell-shaped, a skewed left and skewed right arising. If I go back to our our example right here, notice that this distribution would be skewed left, meaning the tail on the left is longer. That's, by the way, why we like to actually display data in pictures. Visually, it's just kind of nice to see where things are trending. So with dots, all you do is represent dots. For instance, if we have 40 randomly selected households, let's go ahead and draw a dot plot for this. Just like last time, I will be copying and pasting this into Excel. Let's take up a new sheet right here, copy, paste. Remember, you might have to change it because that is my PowerPoint font. We can go ahead and order it. Control X, Control V, Control X, Control V, Control X, Control V. Let me go ahead and bring everything down here. That way I don't have to copy paste for as long. Control X, Control V, Control X. The fun part of the video, right? Control V, Control X, and last but not least, Control V. Whew. From here, since we're wanting to count the number of observations for each different number, we'll highlight all of the data, go to sort and filter, and sort from smallest to largest. That way it's easy to see. Notice that we have 0 observations for the smallest and 5 observations for the largest. So when I go and do this, if I can drag this over, are you really not wanting me to be able to drag you? Grr. Come on now. Okay, well, I'll do this trick. Make it big. And now it's not wanting to go. Okay, we'll just do it right here then. So if I do the dot plot, what I might want to do here, if I go ahead and just insert a new slide, apologies, gotta be resourceful here. Well, first I want to go ahead and list out all possible values I could attain. So we already talked about between 0, 1, 2, 3, 4, and 5. Going back to Excel, notice that we only have one observation that is 0. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 observations for 1. So I would literally go 1 for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for 1, I believe I said. For 2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 different observations. You would put 14 dots right here. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can maybe do 1 dot equals 2. That might be good for you to do here. For threes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. For 4, we have 1. And for 5, we have 2. So thankfully and mercifully, no more drawing dots. That's what a dot chart could look like. Notice that you can see the representation. We kind of have something that potentially tails is skewed right. You could say a little bit longer just because of the 5 over here. That's how you do a dot plot. Hopefully not as bad as, say, a histogram. It's literally just going to be organizing this data. The main things I want you to be good at will actually be these lower class limits, these upper class limits. There will be a problem like this on the exam where you take data that is given in a table and you have to construct these frequency distributions. It will be up to you, given that problem, to be able to say, well, wait a second. That means my class size is between 1 and 3, between 4 and 6, 7 and 9, so on and so forth. We will have more practice over that. I'll be sending out more videos, but that is all I have for this section. So best of luck to you attempting the homework. Reach out to me any questions, and good luck.